All right, let's look at the alternating series test. All right, alternating series test is a series where terms alternate signs. So first, let's say first term is positive, second term is negative, next one is positive, negative, and so on. All right, so the typical notation is summation n goes from 1 to infinity. Negative 1 to the n plus 1. So this part kind of controls the sign of each term. And bn. bn is just the positive part of each term. Then you're going to have b1 minus b2 plus b3 minus b4 plus b5 and so on. So that's an alternating series. All right, so there's a test for that. All right, it says this. If we have these two conditions satisfied. So if you look at the positive part of each term, it's decreasing. So which means this says that bn is greater than or equal to bn plus 1. So as n gets larger, the term is getting smaller and smaller in magnitude. Right? And the second condition is that the positive part of each term, the limit of that has to go to 0. Right? Then if you have those two conditions, we know that the alternating series converges. All right. So this is what the idea behind visually. All right. So let's say you're going to have b1 is a positive term. You're adding b1. So it's going to look like this. So you add b1. So you're going to step forward. All right. So this is b1. All right. All right, then after that, you're going to step backward because you're going to subtract b2. So you're going to step backward. So this way. All right, so subtract b2. Right? All right, and then next one, you add the b3. So you step forward. So this is positive b3. It's kind of hard to see. And then you can see that we keep on doing it, and every single time the step is going to be gradually smaller and smaller and smaller. So you go back and forth, but the step is going to get smaller and smaller and smaller. So you can see that this is going to continue like this. So you're going to go backward a little bit and then go forward, backward, and forward, backward, forward, backward. So eventually you're going to approach some number. So that number is going to be the sum, right? So that's why we get a convergence if we have these two conditions for the alternating series. All right, so let's look at a couple of examples. And first one is called the alternating harmonic series. All right, this is just a harmonic series with this, with the alternating sign. Right? So it's going to go 1 over 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 and so on. All right, so let's apply alternating series test here. All right, so first condition is so Bn is this guy right here. All right, so this is Bn, right? So first we have to show that this guy is actually decreasing, right? So if you look at the Bn, which is equal to 1 over n, right? And if you compare that with 1 over n plus 1, of course the denominator is 1 larger, so it's going to be, the fraction is smaller. But this is exactly the same thing as Bn plus 1. Right? So you can see that this satisfies the first condition. Right? Then you can check the second condition. You can take the limit of Bn, right, as n approaches infinity, right? So this is a limit of, this one's easy, right? 1 over n as n approaches infinity. So 1 over infinity is going to approach 0. So we can see that the second condition is satisfied. So we know that this alternating harmonic series is, this guy is convergent. All right, so this is by alternating series test. right? So that's the conclusion here. All right, so we know that the harmonic series, original harmonic series, is divergent, but if it's an alternating harmonic series, then it's convergent. All right, so let's look at the second example. All right, so we have an alternating series, and we can see that here, this guy is going to be our Bn. All right, since I know the answer, I'm going to actually look at the second condition. All right, if you look at the second condition, we're going to take the limit of Bn as n approaches infinity. But in this series, Bn is n over n plus 1 as n approaches infinity, right? In this one, n goes to infinity and the top and bottom goes to infinity. So I'm going to just multiply top and bottom by 1 over n. Right? Then you see that this is going to be the limit as n approaches infinity. And then you have, let's say, n divided by n is 1, n divided by n is 1, 1 divided by n is 1 over n. Right? So you can see that here, as n approaches infinity, this approaches 0. So what's left is 1 over 1. So this is going to be equal to 1. Right? So you know that this is not equal to 0. Right? So it violates the second condition of the alternating series test. So we cannot use the alternating series test to conclude that it's convergent. So, but this actually implies that you can use the divergence test. So you have a limit of the whole term. So it's going to be negative 1 to the n plus 1 and n over n plus 1. Right, as n approaches infinity, right? So this limit actually does not exist because what happens is this portion of it, n over n plus 1, this guy approaches 1. We just figured that one out, so it approaches 1, right? But it changes sign. So this term is going to be almost like a positive 1, negative 1, positive 1, negative 1. So it keep on oscillating between, positive 1 and negative 1. So this limit does not exist. So which means that this guy is going to be divergent. This is by divergence test. Because the limit of an has to equal to 0 for the series to converge. Right? By divergence test, we know that this is divergent. All right, that's it. I hope that this was clear.